In the previous lesson, we learned about titration of an acid and a base where there is only one Ka or one Kb, and it has only one equivalent point. And we consider those acids as monoprotic. Now, monoprotic acid is basically saying that it has one hydrogen to donate. In this case, we are going to look at a situation where an acid has multiple hydrogen or multiple proton in it. And this acid is considered as a polyprotic acid, or if we look at it in terms of base, it will be a polyprotic base. Well, even though a polyprotic acid has multiple hydrogen, but the acid can only donate one proton at a time. Let's look at this example right here. We have H3PO4. It has 3 hydrogen, so therefore it's going to donate 3 times. Okay, so it's going to donate 3 times. What does that mean in terms of Ka? Well, first it's going to have 3 separate Ka. The first one is going to be for the first H+, and then it has the second one, and then lastly we have Ka3. So each one is for 1 hydrogen ion. But the first one is the most important one because it allows us to find the initial concentration, okay? So this allows us to find the initial concentration of the acid. Before we draw a graph of a polyprotic acid, we need to look at one important term called amphoteric. An amphoteric molecule basically is a molecule or an ion that functions as an acid or a base. And water is a common one. Water can be a base or an acid in different situations. The limitation of the AP chemistry class is that if you look at the graph of a polyprotic acid, can you learn something about this particular acid or base? For example, I'm going to draw you one, and from there, what can you learn about this particular acid, okay? And the first thing we look at the titration of a polyprotic acid is the equivalent point. How many equivalent points does it have? Well, the equivalent point occurred at the steep slope, and right between it, that would be your first one, and here will be your second one, and this will be your third one, okay? And what's so special about that? Well, each one of those represents 1 hydrogen. So I know right away that this particular acid is H3A. It has 3 hydrogen because of the 3 equivalent point. Now, what else do I know? Well, at the first equivalent point, okay, this is the number of moles of OH is equal to the number of moles of the acid. In this case is H3A. And if we look at the second equivalent point, the number of mole of OH is equal to 2 times the number of moles of the acid in this case. And if we look at the third equivalent point, the number of mole of OH is equal to 3 times the number of moles of the acid. What else can we learn about this graph? We can actually look at the half equivalent points. Well, in this case, this is our first one right here, okay? So this is a half equivalent point. It's labeled HE. That's our first one right there. And this will be our second one right there. So HE, this is our second one, and this will be our third one. Well, what's so special about the half equivalent point? Well, at this point right here, the pH, let's label this pH, okay? This pH1 is equal to your pKa1, and this pH2 is equal to your pKa2, and over here, we have your pH3 is equal to your pKa3. So we can actually look at the graph and determine each one of those pKa. And if we know pKa, we can solve for Ka as well. So these are some of the properties of a polyprotic acid that we can determine by just looking at the titration curve of it.